So again, we have two methods. We have the energy method, and then we have the simple structure analysis. Simple structure analysis is going to be the one that includes equilibrium conditions, like equations. We have summation the force in the x equal to 0 and the y equal to 0. And in the z, if you have 3D system, is going to be equal to 0. And also summation of the moment about a point is going to be equal to 0 for all the external forces, including reactions. But once the system becomes indeterminate, it's going to be so tough for you to work on. So in this case, energy method is going to be maybe the easiest way of doing it. So what is the sway mechanism? It means that you're going to have here a moment frame. We're going to push it laterally and see how it's going to fail. And at what force is going to be failing down? The failure here is going to be considered the mechanism, right? Again, the question is how much force you need to push the frame with to develop the mechanism. If you like to use here energy methods, this is what I'm going to be doing. But I'm going to be doing some simple checks with the structure analysis method that you're used to. You understand that you have external work, if you remember this term here, external work and internal work. And the work usually is going to be equal to the force, applied force, times the amount of displacement. I guess in the past, we used to have this surface that we used to talk about, right? So I'm going to put this here. Just give me a second. And then we say, here's a surface. We're going to put here a box like any mass. We're going to put here on the top of it, right? On that surface. I'm going to start here to push it with the force. So we're going to say, here's a force. And this force, let's say, is going to be equals to F. So we're going to say this force here equals to F. You're going to push this, and it's going to displace, let's say, amount of displacement. I'm going to call it here X. The amount of work is going to be equal to F times X. It's going to be the force multiplied by the distance over which you move this object from spot number 1 or location 1 to location number 2. So when it comes to force, I'm going to say the force is pushing it in this way. So I'm going to say force times displacement. I'm going to say in some cases, I'm not going to have a force. I'm going to have rotational force. What's the rotational force for us? I'm going to say rotational force is going to be a moment. So actually the moment you can consider to be a rotational force, if you like to call it this way. So in this case, the moment is not really causing direct displacement or linear displacement. It's going to be causing a rotation. So in this case, the energy or the work, the energy here, which means the work, is going to be equal to this rotational force, which is a moment multiplied by this amount of rotation. So we're going to have external work and internal work. At the end of the day, external work usually is going to be equal to the internal work. They have to be equal to each other. Unless you're going to have some losses, which doesn't apply in this case. And this losses means cracks and damage and this kind of things. In here, in this analysis, it's going to be ignored because we consider it to be very limited. But if you are doing here second order analysis or you're doing research, there's going to be some cracks that you can quantify it with some energy loss. I'm not trying to cover this here. So for me, there is no energy loss. External work is going to be equal to internal work. Now I'd like to see here, how can I apply this principle in this moment frame analysis? This markups is from the previous, right? The previous work that we have done. So let me clean it up a little bit. So I'm going to say here, in this example, I'm going to be pushing the frame, and the frame is going to be shown here with this solid line. This solid line is the original location of the frame, original position. I'm going to push it here with the force F. Now I'm going to have equal displacement at each column. Why? Because this diaphragm or the beam is really strong when it comes to axial compression. So the top of this column is going to be shifted by amount of displacement of delta, which is going to be exactly the same amount of displacement that you're going to have on the second column. Can I give here some symbols? I'm going to say the length, center to center of this is going to be equal to L. The height of the frame is going to be equal to H. boundary conditions. I'm gonna have here simply supported, which means a hinge and a hinge on both sides, or a pin support. The top, I have here fixity between the column and the beam. Therefore, I'm gonna be able here to develop this moment. When you push it, this can be developing here some moment. So, okay. Now let's figure out the moment that's gonna get developed in the column. If you push with the force F, this R is gonna be equal to what? Because I have symmetry in the columns, two identical columns. I'm gonna say this is gonna be equal to F divided by 2, 1/2 of the force, which makes sense, right? So the moment at the top of the column, the moment right here, if you cut a section and take the moment for the forces on this side, so provide I'm gonna be cutting a section for this area here, right? For the column, only for this piece. Don't look at the rest of the frame. You're gonna say the moment at this section is gonna be equal to R multiplied by H. So use the moment is gonna be equal to R times H. But if you like to say summation of the moment is gonna be equal to 0, at this point you need to include all the forces on the frame, which means the other R, and of course if you're gonna have vertical component also here and there needs to be considered. So I'm gonna say use the moment on top of the column is gonna be equal to F divided by 2, 1/2 of this force, multiplied by the column height H. Now, as long as the system is linear, which means it's still elastic, this equation is perfect. Now, once you go here at the yield point, you realize that you push the frame and there is no more resistance. The frame is stopped resisting the lateral force. And the amount of force here is going to be locked to a value, and this value is going to be equal to MP divided by H. Now, what is MP? It's going to be the plastic moment. And how much is this plastic moment? You say, well, to find out the plastic moment, I can just take the section modulus, Z sub X, multiply by F sub Y. Someone's going to say, how about the probable moment? So if you like to call the probable moment, you can multiply by C sub CR and also the R sub Y, the 1.1 and 1.2 max, if you guys recall these two values. So it depends which mechanism you're looking for. Are you just looking for the simple M sub P, or you want it to be to the MPR? In general terms, if no one mentioned anything to you, which moment to be used, it's going to be M sub P, which means ZX times F sub Y. That's it. You don't include the increase because of the expected yield strength, and also you don't include the CPR, which is for the strain hardening of the steel. You don't include any of that. So I'm going to say I'm going to be pushing this with the force F. At certain point, again, I'm going to be reaching the M sub P value. So I'm going to say, is this M sub P is what? I'm going to say this is going to be the property of the column. Meaning, when you're talking here, ZX is going to be ZX of the column. When you're looking at F sub Y, it's going to be F sub Y of the column. Therefore, M sub P is related to the column itself. So it is not affected by the height edge. Meaning, if you take here a short column or a very long column, M sub P, as long as the material is the same and the column section is the same, M sub P is going to be the same. What's going to get changed is going to be this force, the lateral force that we're talking here about. So M sub P is going to be, again, a property of the column. It depends on the column section and the column material. So, okay. Yes, this is clear up to here. Now, when we have this deformation, when the frame is going to start to move, this angle rotation in terms of radians. So again, this theta here is not given degrees, it's given radians. So all our analysis, once you see here, theta is given radians. And this angle rotation, because it's given radians, and also because it's given extremely small angle, it's going to be equal to the tangent of this angle. So theta is going to be equal to tan theta. And tan theta in this case is going to be equal to delta divided by h. It's going to be equal to that length divided by this height, right? This is what you call your tangent of this angle. So I'm going to call here this theta, again, is going to be equal to tan theta. Is going to be equal to delta divided by h. Therefore, delta is going to be equal to tan theta or theta times h. This explains this equation. Are we clear on this or no?
Yes, sir.
Yes.
Okay. So I'm going to say here theta is equal to tangent of theta, right? It's equal to delta divided by h, by the height h of the column or the mount frame. Okay. I guess if you take this equation, right, you can say here delta equals h times theta, which is this equation here. So good. Now, how much is external work? As I said here in the previous slide, I'm going to have two amounts of work, external and internal. How much is external work? I'm going to say external work. Let's look here at the external forces. I have one external force, and I have a shift of delta, just one delta, because this is going to be the same as this. If you like to take 1/2 of the force multiplied by this delta, and then another 1/2 of the force multiplied by this delta, it's going to be okay. But I can just say simply, external work is going to be equal to the force times delta, F times delta, right? And from this equation, delta equals theta times H. So I can revise this equation instead of F times delta, it's going to be F times theta H. This is going to be the external work. I said, okay, good. How about the internal work? Do I have any internal work? What did you develop when you push it with this force here? I'm going to say I developed two forces. It's going to be like reactions. And how about the formation? I mean, when you put these two forces, did you move the support? Did the support move right or left?
No.
No, support didn't move. It's a support, right? It's a hinge. It's going to be in place. But what happened? I have some deformation within the frame. So what happened? The frame itself is going to start to rotate. The columns, the two columns. And each one of these two columns start to rotate by amount of rotation of theta. I'm going to say what is the internal work in this case? I'm going to say for the first column, it's going to be MP of this column times this theta, right? And for the second column, I'm going to have another MP times the same theta, just happen to be the same because the column height is the same and the amount of drift was exactly the same. You say now here is the internal work. Now let me set them equal to each other. So I'm going to say F theta H, which is external work, is going to be equal to 2 times, or MP theta plus MP theta, which means 2 times MP. I guess out of this equation, you can cross out the theta, right? So theta is not going to be really important to us. I don't care about the amount of rotation. So I'm going to have here FH is going to be equal to 2 MP. Therefore, this force out of this equation, this force is going to be equal to 2 times MP divided by H. Right? If I just take this equation, rewrite it, is going to be 2 MP times H. So what did we ended up with here? We were able here to obtain the force, and I'm going to call this the mechanism force. Look at this, determine the mechanism force in terms of MP. What is MP? It's going to be the moment, plastic moment that happens within the column. So I'm going to say this force based on this energy method, right? This force is going to be equal to 2 MP divided by H. So good, all right. So I have here an energy method to find this out for me. But you know what? I should be able here to find out the same conclusion, which means this mechanism force differently. How's that? I'm going to take you back here. I said that I have two methods. I have an energy method and simple structure analysis method. In here, I used the energy method, right? I said, but how about for this example? Can I use the simple structure analysis method? I said, yes, because this is determinate. This is not indeterminate, meaning that I should be able to solve for R if I want to. Because I have here two identical columns, I'm going to say the force at each hinge, at each support, is going to be equal to F divided by 2 and also F divided by 2, just because the two columns are exactly the same. And the moment in here, right, at this location, if you take the moment and cut it, right, it's going to be equal to F divided by 2 times R. So let me write this equation now. You say, based on this equation, when you take the moment, you say MP equals is going to be H times F divided by 2. Are you guys following me? Agree? Or any questions?
All good so far.
You're good? Okay. All right.
Yeah.
Therefore, F equals, out of this simple equation from structure analysis, F is equal to what? This one. It's going to be equal to MP times 2 divided by H. It's going to be 2 MP divided by H. Same equation. So you can reach the same conclusion if you're going to be doing here structure analysis method, if we do energy method. Just because I have determined structure and the structure was really simple. But if you get to a complicated structure, the energy method is going to be much simpler. So here, when you look at this, you say, why would you do all of this? I could have just done it this way. I'm going to say, yeah, this makes sense just because the structure is simple. But if I give you here a little bit complicated structure, you're going to say, no, let me just do the energy method. Are we good? Any questions?
No questions
No?
at the moment.
All right, great. All right. Now let's make it a little bit tough. So I'm going to be taking here different structure. I'm going to have here fixed. I'm going to have here 2 fixed points. Columns are identical. I'm going to start to push it. So I'm going to be pushing here the frame with a force F. I'm going to have delta and delta. They're going to be exactly the same. The column is going to be equal to height is equal to H. And in this case, because it's just going to be one column, at one point, I'm going to be able here to developing this plastic hinge, top and bottom. So I'm going to say plastic hinge is going to be here and there. What does it mean by plastic hinge? It means I'm going to be approaching M sub P value. This is where the plastic hinge is going to start to occur. And look at the direction of the moment. Usually the tail is going to be in the tension side of the moment frame. So in here, tension is going to be right here, the outside. Just imagine that you push the moment frame. Tension is going to be here. And in this side, tension is going to be here. Look at the arrow. Is it okay? Looks very simple to me. Now, external work and internal work. You can say here, external work. I guess this equation now is known, right? Delta is going to be equal to theta times H. We did this already. And I can just repeat using it if I want to. External work is going to be equal to this force times delta. It's going to be the same thing. There's no difference. It's going to be the same thing. Very similar to the previous example, right? Which means F theta H. How about the internal work? I'm going to say in here, I'm going to have a theta, right? But I have 2 moments. I have moment on the top, moment on the bottom. So in this case, for the first column, I'm going to have 2 MP times the angle of rotation theta. The second column, it's going to be exactly the same. Now, set the internal work to be the same as external work, right? What's going to happen? F theta H is going to be equal to 4 times MP theta. Again, cross out theta, and this theta. Going to have FH equals 4 MP. Therefore, F equals 4 MP divided by H. Done. Nice problem, I guess, right?
So the only difference, Professor, is that this is an indeterminate structure and
this is indeterminate plus symmetrical, so it is identical. It's going to be only 2 columns, same height, same material, same length. And when you have fixed T here at the bottom, you should expect to create or to develop MP at the bottom and the top. And here I have only 1 MP on the top of the column because of this fixed T to the beam. But in here I have 1 MP at the top, connection between beam to column, and also at the bottom when you connect the column with this fixed T to the foundation.
oh, okay, so it has to do with the type of
The clamping or the boundary conditions, right?
Yeah. Okay, thank you.
Yes, all right. Very good. Let's push it a little bit. So now I'm changing here the column height. You push the moment frame with this force F. This column height is 9 feet, and this column height here is 6 feet. The top displacement is going to be the same because this beam here is rigid, right? Here's the beam. Here's the beam length, right? You push it, it's going to get moved here. Same length. So this amount of displacement is going to be the same as this amount of displacement. But look at what happened. This angle of rotation is going to be different. Now, which one's larger? Is it theta 1 or theta 2? Just for curiosity here.
2.
Theta 2 is going to be larger. Why? Because the column is shorter. This delta here, as we said in the past, is going to be equal to theta times h. So I'm going to say here, this delta is going to be equal to theta 1 times h1, 9 feet. It's going to be 9 times theta 1. It is also equals to 6 times theta 2, right? It's going to be 6 times theta 2. It's the same delta. Therefore, I can find out the relation between theta 1 and theta 2. Look at this equation here. Just take it and move it here, right? Now, which one's larger again? We say theta 2. So theta 2 is going to be equal to 9 divided by 6. It's going to be 1.5 theta 1. Now I have a relationship or a ratio between theta 1 and theta 2. I guess in my analysis, I can just use one of the thetas, right? But let me do first the work thing that we have been doing here. External work is going to be equal to F times delta. I'd like to use theta 1 in my analysis only. I don't want to see the theta 2 because otherwise I'm going to have two variables. I'd like to simplify it. And the good thing, I have a ratio between theta 1 and theta 2. Let me take the force here times the displacement delta, which means F times. Now, how much is this delta? I'm going to say 9 theta 1. So I'm going to say it's going to be equal to F times 9 theta 1, which is the amount of displacement that you have here, the drift. It's going to be, that's it. I don't really need to care now about theta 2, right? It's going to be just the force times the displacement. About the internal work, I'm going to say internal work, I'm going to have 1 MP developed here and 1 MP developed here. But this MP is going to be creating a work or energy is going to be different from the energy on the other column. Because this MP is rotating this column for theta 1, and this MP is rotating this column with theta 2. If you like to look here at the internal work, you see in the first column, what do you have? You can say MP times theta 1. Yes, because it's going to be the same column. I'm going to say same column meaning the same MP because the column of the same material and same cross section. In the second column, the energy is going to be equal to MP times theta 2. Okay. Do I have a ratio between theta 1 and theta 2? Because previously I said I don't want to see the theta 2 in our analysis. We're going to say, you know what? Theta 1 equals to 1.5 theta 2. Look what happened. Here's what happened. Here's 1.5 theta 1 multiplied by MP. And this is theta 2. And for the first term, it's going to be yes, MP times theta 1. External work or energy is still 9 theta 1. I guess if you have here MP times theta 1 plus 1.5 MP times theta 1, it means that you have a total of 2.5 MP times theta 1. I'd say cross out theta 1 with theta 1, right? I can cross them out. What do you end up with? You're going to say here F times 9, right? So it's going to be 9F equals 2.5 MP. Yeah, makes sense? I can clean it up a little bit. It's going to be 2.5 divided by 9, which means F equals 5/18 times MP. And with that, I'm done with the mechanism force in terms of MP. Questions? No questions?
No, that was really clear. Thank you.
All right. Okay, good. Thanks. Now, let's change the variables a little bit. Now, let's get an actual column size. And I guess this is what you should expect in your final, right? Let's give you like some numbers. It's not going to be all symbolically, like symbolic analysis. We need to see some numbers, at least to make it easier and more exciting to us. So I'm going to say in this example, we say determine the mechanism force F. How much force is needed to fail the system? Because mechanism meaning what? You're going to have loss of displacement and no resistance. So what's the maximum force that you can put in there? First column is W12 by 120. Second column is different. It's 14 by 132. Column height, hinge, and a hinge, and the distance is going to be 8 feet. You think that this spacing between the column is going to be critical to us? Say, not really. Here's the first column, W12 by 120. You have the ZX. You can just look it up in the table. It's going to be 212. Second column, also same thing, ZX. Look it up. MP for the first column, I'm going to call it here MP1 for this column here. It's going to be equal to what? ZX times F sub Y. And I like to develop here, but divide by 12 to put it in kip-foot. Reason because the height also is going to be in feet, right? So I'd rather keep everything in feet. Same thing for the second column. You have the ZX times F sub Y, divide by 12 to put it in kip-foot. Any questions? We're good about this MP calculation? Two different columns? All right. What's next? Now, next I need to do external work and internal work. Okay. This amount of delta, if you remember, is going to be equal to 6 times theta 1, and it's also equals to 12 times theta 2. Now, which one's larger? Is it theta 1 or theta 2? You can say theta 1 is going to be much larger. By how much? By the ratio of this 6 feet to 12 feet. The inverse of it. Which means that theta 1 is going to be twice as much as theta 2. Or theta 2 is going to be equal to 1/2 of theta 1 from this analysis. It's going to be very simple analysis. Depends on the ratio of the column height to the column height. Just because the amount of drift that you're going to have on top in both columns is going to be exactly the same. Beam assumed to be compressionless. It's going to be exactly the same length. Now let's look here at the external force. I have one external force, amount of delta. Therefore, the external work is going to be equal to F times delta. And this delta is going to be equal to 6 theta 1. And here we go. Here's the external work. Good. Simple. How about the internal work? I'm going to say, you know what? There is no moment developed at the bottom. Only moment developed on the top. This moment, I'm going to be calling here MP1, which is the same as this, right? And the second moment is going to be MP2. Now, let's find out here the energy or the internal work is going to be MP1 times theta 1 plus MP2 times the theta 2. Also, we have the ratio between theta 1 and theta 2. We would like to keep everything in terms of theta 1, just for simplicity. Say, okay. External work. Here we go. This is going to be the external work. It's going to be this box, right? Equals to the internal work. MP1 theta 1. MP1 as a value is going to be 883. MP2 is going to be 975. So here we go. Here's MP1 and here's MP2. Theta 1, just use it as is. How about theta 2? I would say let's put in terms of theta 1, it's going to be equal to 1/2. Let's say here we go. This is going to be what? Theta 2 that you have in your analysis. Now let's clean the equation a little bit. See the number here, now start to see not simple numbers like what we have looked at here, right? I start here to see some numbers, right? Actual numbers. If you look at this equation, it's going to be 6F theta 1 equals 1370.83 theta 1. Can you cross out theta 1 and theta 1? Yeah, you just get rid of them. Now what you end up with? 6F equals to this number. Therefore, F equals to this number divided by 6. And here we go. Now we know how many kips is needed to create the mechanism in this moment frame. And what's the mechanism? Mechanism means, definition of mechanism, to form 2 plastic hinges, in this case for this specific frame. And in this case, once you reach this mechanism force, just the moment frame is going to be collapsing. It's going to be reaching the maximum value that it can ever get to. I'm going to say you can call this going to be the mechanism force or the collapse force. So once you get to this force, moment frame is going to be falling down. Questions?
Sir, if we suppose the moment force is 228.47 kips, and if our answer is coming for our frame 200 kips, then should we increase the number of W or should we keep it the same?
Are you saying if the force amount of force that you push the moment frame with is 200 kips?
Yes, sir.
Okay. You mean like with seismic analysis? Am I correct?
Yes, sir.
Okay. You understand that we have this strain hardening in the steel. Am I correct? No. Do we know what is the elastic hardening or strain hardening?
Sorry, sir, I don't remember it.
Just looking for something here to show you. Just give me a second, please. It's right here. Let's give you this slide. This is exactly what I need here. If you like to consider your stress-strain relationship to be plasto-elastic, which means perfectly plastic and it's going to be elastic, means that performance is going to look like this. This is elastic, perfectly plastic. You see this, what happens? I'm just ignoring the strain hardening, right? You follow me, Maheen?
Yes, sir.
Yes. So if you consider that you have elastoplastic performance, the moment frame is going to be failing in this case. But the good thing, we have this strain hardening. So what does it mean by strain hardening? It means that the moment frame is going to be going through this yielding process, is going to be going to the plastic performance, and then at certain points, it's going to start to pick up some force again. So it's not really failing, right? So in reality, it is not going to be really failing. But if you consider the performance to be elastic plastic or elastic perfectly plastic, this is what's going to happen. It's going to be collapsing, and this is what you call here mechanism. So in reality, the moment frame is not going to be falling down. In reality, the moment frame is going to continue to perform as long as you're not reaching this point. If you're going to be within this range, everything is going to be good, right?
Okay.
If we're going to be within this range, let's say up to here, right? If the strain is going to be within this range, your moment frame is going to be okay. There shouldn't be a problem with that. So it depends on the problem. Is the problem done here for academia, or the problem is going to be done for an actual design? If it's going to be done for academia and you consider elastic perfectly plastic, it means this is going to be the mechanism force and the moment frame is going to be collapsing. If you're doing it for design purpose, so in this case, you say this mechanism, right? It should be very close from the design force. Because what we'd like to do, we'd like the strain in the actual performance of the structure during an earthquake, we want it to be in this range. You want it to be close to the strain hardening, which means we want the moment frame to go into the plastic performance and go a little bit very close to the strain hardening. This is gonna be like the desired performance. It doesn't mean it's gonna be failing down, but all what it means is gonna be showing some strains, right? But it's not gonna be collapsing, and the system is gonna be standing still in place. Okay.
Okay, sir.
So this analysis that we are doing here, we're just here exercising how do you do this plastic analysis of moment frames, and what does it mean by it? Good question, Maheen. Thank you. I'm gonna be moving here to two-story moment frame. And I did here a relationship between, or in the first floor, I'm gonna have here a force F. On the top at the roof, I'm gonna put it at 2F, just twice as much. And I put this here to be hinge. And the top, of course, I'm gonna have fixed T. So thinking here, which moment is gonna get developed, I'm gonna say I may be able to develop a hinge here, right? A hinge here, because column is gonna be the same, right? Same thing here, same thing here. And column size gonna be the same in both levels. Plastic hinge here, and a plastic hinge here. Can I add a plastic hinge here?
No.
Why not?
Because there's already a support
Yeah,
attached.
it's
to
already
it.
hinge. It's already hinge. So, I mean, yeah. So what does mean by this big circle versus a smaller circle above? Does it mean anything? No, just a plastic hinge, right? So I don't want anyone to come back and say, how come this looks like an oval shape and this like a good circle? Means nothing. It's just my drawing. So I'm gonna say, okay, so I'm expecting moments to happen at these locations to create the mechanism. Now let's look at the moment. Look at this. Where's the tension side? I'm gonna say tension side is gonna be here. When you draw the moment, you draw the moment so that the tail is giving the tension side. So we're gonna say here I'm gonna have MP, and I'm gonna have 260 for the column. It's gonna be MP in the top and MP in the bottom of the column. Okay, good. I have the column height here. This here 16 feet, 11 feet, and 11 feet. Now let's look at the deformation. This amount of delta in the top, you can call it here delta what? Delta 2. So this is here delta 2. Let me type it here. At the bottom, it's going to be delta 1. Whatever happened in the first column is going to be the same as the second column. And the angle here, if you like to draw it as a straight line, this would be fine. I mean, nothing's wrong with this, right? So this displacement here in terms of this theta, you see here you have one angle, theta and also theta, because the two columns have the same height. So this displacement, delta 1, is going to be equal to 11 times, 11 is the height, times theta. And the big displacement at the top is going to be twice as much. It's going to be equals to 22 times, which is the total height times theta. Okay. So theta is going to be the same in both columns. It's not going to be different. It is unlike this problem here that you have two different angle of rotation. Here is going to be the same theta. You see, now let's look at the external work. I have two forces. I have the first one here, F, multiplied by delta 1 to give you the first energy, external energy. The other energy, external energy, is going to be coming from this 2F times the second delta. So just say for the top, the 2F, take 2F multiplied by 22 theta, right? Which is this displacement. For the bottom one, it's going to be F times 11 theta. You say all of this is going to be all external work. I can add it up together, right? So when you add it up together, what would you end up with? You say you end up with, look at this, it's going to be 11 plus 44 is going to be 55. Okay, good. 55, yes.
Quick question, sorry. Why isn't the 11 theta multiplied times 2?
Okay, very good question. Times 2 because you have two columns? Are you asking because you have two columns?
Because I assume like you were gonna multiply it twice, like 2f theta, like in the example 3. How come it wasn't 2f 11 theta?
Let's go to 11, example 3. All right, very good question. In here, I multiplied just F times 1 delta. I did not multiply it twice for the external force because the total external force in both of these two columns is equal to F, right? So
I
you
meant
have the
example
total.
2.
Example 2.
Sorry.
Okay. I have one force F. I just multiply by delta. And with that, I have the total external work. I didn't multiply by twice by 2 because it's just one force and one displacement. If you want to do it for each column separately, this would be fine. But I'm going to say, you know what? Find out the force in this column multiplied by this delta. Find out the force in this second column multiplied by delta. How much is the force in this column? It's going to be R. And R equals, if you remember, F divided by 2. So in this case, you say F divided by 2 times delta plus, again, F divided by 2 times delta, because you have two columns, right? So I don't really need to multiply by 2 if I'm going to be taking the entire force times this delta. As if you have one object. If you remember this problem here at the beginning, I'm sorry, I deleted it. Let's say that you have, I'm going to draw it here. You have one object here, right? And here's the bottom. This is the base of it. I have this object, and this could be the surface, right? Follow me, Elizabeth? I said, okay. I'm gonna push it here with the force. So here's the first initial location. This is gonna be the final location. Let's say it just moves laterally, but I'm just showing it here to be a little bit above it so that you feel, yeah, it is not the same box, right? The first end moved by how much? Delta. The second end moves by another delta, correct?
Yes.
Yeah, but the total energy in this case is going to be equal to this force F times 1 delta. Yes or no? Clear?
Correct.
Yeah. So actually, when you look at this, it's going to be only one force times delta. It is not one force times delta plus another force times delta. Okay, so now we're clear on this. Now let's go to the last example. The last example here, I said this force here is called 2F. So if you put here, let's say 1 kip, you put here 2 kips. This is the way we're going to be applying the force. If you put here 100 kips, you put here 200. If you put here 1,000, you put here 2,000. And
Oh,
this
right.
displacement, yeah, this displacement here, right, is equal to delta 1, which is 11 theta. Displacement here is going to be 22 times theta, right? Now, you don't multiply by 2. You don't say I have 2 columns because it's going to be one displacement. Very similar to this concept, right? It's true that when you look at it, you feel that I have one delta here, but actually it's going to be only one delta that caused by this force F, right? So I said, okay, here's the first, or the top, if you like, the first force on the top. So this is related to this guy here. Yes, sir. So what happened here? It's going to be 2F. It's going to be this force times 22 times theta, the top displacement. For the bottom displacement, which is only 11 theta, I'm going to have a force of only F, which is this force here, F. I have total of, if you count here, 44 plus 11 is going to be 55, which is this 5F times 11 theta. How about now internal work? How much is internal work? You say for each one of this column, right? Theta is the same throughout the entire column. We agree on this, right? Yeah, okay, yeah. So for this theta, how many moments do you have? How many MPs? I'm gonna say I have 1, 2, 3 times theta. Correct?
Yes.
Are you sure? It's gonna be
Well,
1, 2, and 3.
it's probably, it looks like a couple, one on top.
Yeah, I have 1 times this theta, correct? Where do I have it here in this equation? I'm gonna say here's the first one. Okay, so this one is which moment? This one belongs to this moment. Okay, and then I have 2MP times theta. Where do you have him? I can say here we go. Which is what? Which one now? Let's give you the 2 top MP. And because I have 2 columns, multiply by 2. So if you like to look at this equation, this is fine. You can just look at this column here and just say, how many MPs do I have? Because theta is the same. I'm gonna say 1, 2, 3 times theta plus, I'm gonna say another 1, 2, 3. Total of 6 MP times theta. Look at this, 6 MP times theta, because you have 2 times 3. So I ended up with the same number, 6 MP times theta. So if you like to take each moment, like MP multiplied by its own theta, you're fine. But if you like just ignore this, I'm okay with this. I mean, you just count here. You say, I have MP, MP, and MP. 3 MPs times theta times 2 columns give me 6 MP theta. Done. Now let's look here at the equation. Theta is the same. I can just cancel it, cross it out on both sides. So you end up with MP equals, or F is going to be equal to 6 divided by 55 MP. This is going to be the mechanism force. Any questions?
No.
All right. So which one would you like to see in your midterm, in your final? Sorry. In your final. Would you like to see something like this? or something like this.
Example 4.
Example 4 is a good one, right? It has some numbers that you can exercise and do MPN. Okay, let me write this down. I don't want to forget it.
Yeah, number 4.
All right, cool. Does it matter if I'm going to put here a third column?
That's a good question.
I'd like to hear from you guys. You tell me. Unless I'm going to make it here fixed.
That would be,
That would be what?
if it isn't fixed, it would be just 3 MPs. But if it's fixed, it would be 4, right?
Yeah. How about if I also put a new column size? So you have W12 by 120. I'm going to make it, let's say, by 114. Different column. Would that be interesting problem?
Yeah, it'd be interesting.
Okay, great.
But
So
it
I
will
guess
also make the
now you
question
know.
hard.
Yeah, but I guess now you should be able to go back, right? Once you're done, just create a problem like this and solve it. And just expect that maybe this fixed here, I can maybe move it here or here or here. Maybe all of them is gonna be fixed. Maybe 2 of them is gonna be hinged and 1 fixed. Maybe 2 fixed and 1 hinge. Different size, different height, and solve for this mechanism force. Guarantee problem. You can just make it. You shouldn't miss it. You're fine.
Professor, since we're talking about the final, do you know how many problems we're gonna have on the final or not yet?
No, not yet. How many you want?
Well, if it's about how many I want, I wouldn't want any or just the one. I mean,
All
I'm
right.
okay with having just the one, this one. That would be simple.
You like this? Would the analysis be different?
If the force is still in the same direction, it should be exactly the same.
I mean, would the analysis be different from this analysis that we're just going through it? If instead of having this to be the columns, give you like the beam, we just rotate it here 9 degrees?
No, that should be the
It wouldn't. It is exactly the same. If I'm going to do it this way, look at this. You put it upside down. Would that change your analysis, this force, amount of force F? Say, of course, no. All right. Just give you an idea what you're going to see in the exam so that you're not surprised. And I was going to say, oh, we haven't seen this before. It used to be for the column. Now I'm going to just rotate it 9 degrees.
Professor, like if it be the beam, do we worry about like the gravity from the
No. Gravity is not included here. Don't think about gravity. Just do the same method. It's going to be exactly the same method. Okay?
Yes.
Okay, very good. I'm done for the day. I'm just open here for questions.
So, Professor, the final, is it
Yes.
going to be comprehensive?
Yes, absolutely.
So with the midterm 1, midterm 2 is included.
Absolutely. The whole thing is getting included.
Professor,
Yes.
in the submittal, what is the type of connection we have between the beams and the columns, and what are the columns' final support? Are they fixed
Which one are you
support
talking about? For
or
the moment frame? Are you talking about the moment frame or the typical connection, the standard beam to column connection, or beam to beam?
in the submittal course project?
Which submittal? The upcoming one? The
Yes,
one
sir.
for this coming. Okay. For this coming one, not going to ask you to do the connection, but generally speaking, the connection moment frame, it has to be fixed connection, like moment connection. All right? It has to be fixed connection.
Okay.
For the you were talking about some kind of like appointments for the office hours that you were gonna pick like alphabetical order. Is that correct? That to go over the submittals?
Okay. So what we said Did you join late or something, right? Okay.
No,
Okay,
but it was
so-
unclear after.
Okay.
it's
All
voting
right, no
after the
problem,
call.
no problem. Yeah, this is actually the right time to ask this question, right? So what's gonna happen? We have here certain order, right, for this list. So what I'm gonna be asking you, starting this Monday, you're gonna be joining the class, the regular class, which is the same meeting as this one, right? And then you're gonna be waiting in the wait room. And then I'm gonna bring Mr. Abidi first, and once I'm done with them, once we end up with our discussion, he's gonna leave, and then we'll bring Mr. McGreen, for example. Once he's done, so everybody's gonna be waiting in the wait room. If you're at the end, you don't want to join from the beginning of the lecture, it's gonna be okay. Because I'm not gonna be done with everyone, right? In the same day. But you would rather maybe just be there just in case. If one of you is not available, I'm gonna take next and next and next. So I don't want, for example, are you listening? I don't want people, let's say at the end or the middle, not to be there on Monday and just ignore it and say, you know what, he's not going to be done with 100% of the people or maybe 50% of the people in the first day. So let's not be there, because what happened if one of these people here is not present? I'm going to be taking the following person. So what I'm saying, please, this coming Monday, everybody come to the same meeting, to the same lecture, and just be in the wait room. Okay, just to stay there. I'm gonna be taken one by one based on this list. I'm gonna be going in this order. Does it make sense? Yes.
Yes.
Yes, sir.
Thank you.
Okay.
Yes, sir.
Great.
Professor,
Yes, Mike.
about Wednesday of next week, if we talk to you on Monday, do we show up on Wednesday, or is next week solely about discussions?
Okay. Monday and Wednesday is gonna be for discussion and for review. It's gonna be the final review because now I'm done. I'm done with the material. And for good evaluation for you guys, I'd rather keep the last week for just talking to you.
Okay, so we want to show up on Wednesday for the review of the final.
Yes. Show please. You need to be there Monday and Wednesday, please. Yes, both days.
Okay, thank you.
No problem. More questions?
No, I think that's it.
All right. All right. You guys have a good night. Please sign out. And please start to study. Get ready for the final.
Professor, in the final, should we prepare theory from the first lecture till the last lecture, or like last time it wouldn't
It's gonna be a
contain what-
comprehensive. Comprehensive means it's gonna be covering everything,
Okay,
everything that you have studied. So you need to study the whole thing.
okay, sir.
All right.
Good night, Professor.
All right. Good night.
Have a good night, Professor. Thank you.
Good night, Mike.
Good night, Professor.
Good night.
Thank you, Professor. Have a good night.
Thank you. Good night. Good night, everyone.